Hi everyone, my name is Miss Kay and I am excited to share with you a whole bunch of information about kinetic theory. So whether you are from my specific class or joining us from some other class, welcome and let's talk about kinetic theory. So you should have started the packet at this point if you are specifically in Miss Kay's chemistry class and you know some information about gas particles right now. So what I want to start with next is I want to start with a little video called the molecular motion tube. So you're following along, this is on page 1. So let me show you what I mean. What we have here is a test tube that's got some mercury in it. Mercury is liquid at room temperature, and then it's just got some glass beads. So right now, those particles are liquid and these particles are solid. These liquid particles are in motion and the solid particles are vibrating in place. But what we're going to do is we're going to add some heat. So in the form of a Bunsen burner, you'll see that. So we've got mercury, glass beads, and they're going to use a Bunsen burner to add energy. Well, when particles have more energy, just like when people have more energy, you tend to want to move more. So these particles are going to start moving more than they were before because they have more energy. So we'll see that. You can see that these are starting to move a little bit, and then suddenly those mercury particles don't want to stay liquid, they want to move around, they have more energy, and some of them might actually turn into gas. So that is the idea of the molecular motion tube as related to mercury. All right, so at this point you want to pause the video and then go ahead and continue through the packet. Come back to the video when you're ready for diagrams on pages 2 and 3. All right, so you've learned a little bit more about some of our particles, so it is time to continue our knowledge with these two diagrams. So this diagram is for page 2. You can see that you've got two different gases. T2 is the red line, and then T1 is the blue line. This is the number of molecules. As energy increases, you can see the difference. So two different temperatures, and you can see that the amount of T2 gets to a higher temperature than T1. So that's what that is showing. So take a look at that and answer those questions. When you're ready, here's the diagram for page 3. You have 4 different gases all at the same temperature, and then so the red one versus green versus purple versus blue, so they're all at different, the amount of particles at different speeds. So this is how much particles you have, and this is the speed they're at, versus this is how much particle you have, and then this is the speed they get to. So go ahead and answer the questions that go with that. Take moments to look in here. If you have different colors, that's kind of useful to see the different colors there. So diagrams A and B on pages 2 and 3 of your packet. Go ahead and copy those down. Pause the video if you need to so that you can see everything that's going on. All right, when you are done copying down those videos, when you're done copying down those diagrams, you'll again pause the video so that you can continue through those pages 4, 5, and then when you get to page 6 about tire gauges, you'll check in with me and I've got another story for you. All right, welcome. We've got our next topic is tire gauges. So what a tire gauge actually measures, so you can think of this is the way they look, you put them on the valve on your tire, it pushes out this little thing. What it's actually measuring is the difference between the inside pressure and the outside pressure. The reason we want to talk about this is in Minnesota especially, the pressure of your tires changes a lot within the year. Think about the difference between July and January, just those 2 months here in Minnesota. In January, generally the temperatures are lower, so there's lower pressure because the energy of the air particles is less. So they're moving around less and they are slower, and they're going to have less collisions to cause that pressure. Versus in January, generally higher temperatures, higher pressure because the particles have more energy. So the idea here is that if you are not changing the pressure inside your tires to match for the changing of the outside atmospheric pressure, you end up with really big changes. Your tires can actually push either against the air pressure in, for example, if you don't change the pressure in January, if the temperatures and the pressures around the tire are too low, the pressure in the tire will want to actually push out. And then the opposite, if you don't add pressure in July, your pressure outside is really high, it's going to want to push on those tires. And that in and out, that actually can make your tires expand and contract. And this is maybe why you've seen these tire shreds on the side of the road. It's usually not from cars because we're pretty good at changing, or the temperature and the pressures change slowly enough that we can kind of get used to it. But think of a semi truck. In one day, they might start in Florida and end up in Ohio. The altitude changes can affect the pressure, the temperature changes can affect the pressure, and sometimes those tires just, they can't handle the change so fast and over so much time, in and out, without actually changing the pressure on the tire, that the tires can actually explode. So that's the one reason we might care about tire gauges here in Minnesota. So an application of chemistry and something you very much care about, your tires and your vehicle. All right, go ahead and continue through the packet. Pause the video for now. And when you're ready, after you've read a little bit about barometers, we will continue with speaking of mercury. Okay, so the first thing we want to clarify is, why were we speaking of mercury? So you've got this old-fashioned version of a barometer that's got this pool of mercury with an inverted tube. So it's closed on one end, open on this end. When the air pressure pushes down on the mercury, if there's a lot of pressure, it pushes down on the mercury a lot, and that pushes a lot of mercury up the tube. So inches of mercury or millimeters of mercury is talking about how much mercury is up the tube to relate how much air pressure there is. If there's not as much pressure, it doesn't push as much, so there will be less millimeters of mercury or inches of mercury in that tube. So that's why we were talking about mercury. However, mercury is super interesting to think about. First of all, it's got one of those sort of uncommon symbols. It's Hg, which is the Latin word for hydrogyrum, which is where that comes from. So the Latin word for mercury is hydrogyrum, Hg. That's where that symbol comes from. The other connection is something that you might have heard from, classic fairy tale Alice in Wonderland, the Mad Hatter. So the Mad Hatter was referred to this because there was this job back in the days when people dressed fancy, like old-fashioned top hats. But these fabrics of these top hats would get wilty after a while, and they would lose their shape, and they would kind of like fall over, and that didn't look very good. So hatters actually had huge tubs of mercury that they would just scoop their hands in and then spread on the inside of the hat, and then that would dry and get stiff, and it would keep the shape of the top hat much better. Well, the idea here is those hatters that were doing that, they were actually having mercury particles soaking through their skin pores, and as soon as mercury comes into contact with water, it turns into mercuric acid. Well, of course, there's lots of mercury or water in our bodies, so as soon as the mercury gets through our skin, it creates that mercuric acid, and there can be lots of health problems, especially because think of where they're wearing it. It's right on their head. So as soon as the mercury particles went through their skin, into their skull, into their brain, and the water there, the acid starts kind of eating away at their muscle or their brain connections and brain cells, and making them act mad, like crazy. Like literally their brain is being eaten away by this acid, so they started to act crazy. So this is nothing to be messed with. This is why you no longer see mercury thermometers around schools. Generally, you don't see them anywhere. Now, if you just have a little bit of interaction with mercury, not so big a deal. Like maybe if you ask some of your older like aunts and uncles, or maybe even your parents, they maybe talked about a chemistry teacher that poured a little bit of mercury on their table and they batted around a little bit. If that was the only interaction they ever had with mercury, probably not a big deal. So I don't want you to freak out and worry about your family going crazy. But there was, not that long ago, there was this woman who was studying mercury, and she knew that mercury was dangerous, but she was trying to study some of the effects of it. So she was wearing gloves and making sure she didn't come into skin contact. It turns out, though, she started to, get sick and started, kind of acting as if she had Alzheimer's. And within a month, she happened to pass away. And it turns out that the one box of gloves she happened to have was defective. So that whole month, when she thought she was being really safe and protecting herself, those mercury particles were getting into her body and creating that mercuric acid and causing all of those problems that the Mad Hatter was known for. And then within a month, she passed away. Her body couldn't handle all of that mercuric acid. So obviously an extreme example, but just sort of kind of the amazing level that mercury and other chemicals can have if you're not careful with it. So again, a little bit of a side story, but definitely interesting to think about since we're talking about mercury. All right, thanks for listening. Go ahead and pause the video for now and continue through your packet. I'll check in with you again when you get to page 9. All right, welcome back. So imagine this maybe has happened to you with rubbing alcohol, like maybe you've had to like clean something on your skin, or maybe you're trying to wash off like a permanent marker, or maybe you got fingernail polish remover on your skin and it feels really cold, really fast. Well, the reason that is when it's because it's evaporating very quickly. And when something evaporates, it actually is a cooling process. This is why it's good for your body to sweat, because then the sweat will evaporate and that actually cools down your body so your body doesn't overheat. So just to make sure we understand why evaporating makes you feel cold, here's the idea. Imagine that this is what was happening on your skin. Here's that liquid, whatever it is, like rubbing alcohol or fingernail polish remover or something that evaporates quickly. These particles have energy. The energy from your body heats up that layer of liquid that's on your body, whether it's sweat or rubbing alcohol or something like that. And the energy from your body gives those particles enough energy that they actually leave. So the highest energy particles are gone. Well, the ones left over are lower energy. So the effect is if it's lower energy, overall the temperature feels lower than it did before. So then it feels colder. So that is why evaporation is actually a cooling process. All right, go ahead and pause the video for now. Asking any questions along the way, checking in as you're supposed to. We'll check in again when you get to page 10 about dynamic equilibrium. All right, so you must be ready for some dynamic equilibrium information. So I'm going to show you a video and kind of talk about what's going on here. So let's check this out. So dynamic equilibrium. So what we have here is a tub of greenish water pretending to be reactants in a balanced equation. And then you have this thing pretending to be the products in a balanced equation. So what we're going to do is equilibrium has to do with sort of a balance. So dynamic equilibrium is going to eventually show sort of a connection between reactants and products, or think of it as evaporation or vaporization going from liquid to a gas, and then condensation going from gas to liquid. So this works for reactants and products. It also works for these phase changes. So we're going to call this our liquid, this our gas. So right now, you're going to scoop from each one and put it to the other. Well, notice not much is coming out of here because nothing has turned into a gas yet, and it pours in there. Oh, but look, now some has turned into a gas, so now some can start going this direction, but not as much as it's going from this direction to this direction. Now it continues, so you see that after a while, I can start to put more from this direction and then more from this direction. This is still pretty much the same. But eventually you get to the point where almost the amount that is going this direction is the same amount that is going this direction. That is dynamic equilibrium. So if you watch now, we're kind of at the point where these levels are not changing much anymore. The amount that is going this direction, so if we think of vaporization, the amount of going from liquid to gas is the same as going from gas back to liquid. That is called dynamic equilibrium. And that would be what would happen in a closed system where these gas particles can't leave. They're just going up into the air or above the liquid, and then they can't leave, so they go back down into the liquid. So get liquid to gas, gas to liquid. Dynamic equilibrium is when the same amount is going back and forth, back and forth. That is what dynamic equilibrium is. All right, thanks for listening to that and kind of watching that demo so you kind of get an idea of what's going on. So that's on page 10, so go ahead and fill in any information about that, ask any questions about it, and then we'll go ahead and pause this video and come back to it when you're ready about to talk a little bit about a vacuum pump. All right, so welcome back. So the first thing we just got to clarify is just what is a vacuum pump. So it's called a vacuum pump because once you turn it on, it pulls out all of the air particles that are inside. So if there's no air particles in there, you got to think, okay, well, if there's no air particles inside this bell jar, then there can't be any pressure. No particles, no collisions, no pressure. So really what we're doing is we're going to talk about water, how it would be affected by no pressure around it. So let's take a look at this video. So here is my vacuum pump. I've got some water in there, and then they're going to show what's happening here. So I'm going to pour some water into the beaker. So just some room temperature water at this point. And then we'll put the bell jar on top of it just to create that vacuum space. And then turn on the vacuum. And then when the vacuum is turned on, we can see that the pressure is getting lower and lower and lower because there's no particles left in there. So right now the temperature isn't changing. It is still room temperature. Nothing is changing about the actual temperature of the water or the air pressure or anything around it. But look at, suddenly that pressure, that water is starting to boil. So think of it this way. There's pressure inside the liquid. So there's pressure inside the liquid, and that pressure is no longer being kept down by the pressure of atmosphere around it. So if I remove this pressure, the pressure inside here, those air particles between the water particles, they want to leave. So they now can have enough energy to leave. There's nothing to hold them down. And this is the idea of using a vacuum to actually make something boil without changing the temperature. So seeing that for a few more moments. That is what we're looking for. All right, so back to your packet. Go ahead and talk through that idea with your group. See if it makes sense. Ask any questions as you have it. But then go ahead and pause the video, and we'll see you back here when you're ready for page 11. All right, so this one is one of these great examples of not magic, it's science. So I'm actually gonna boil water with ice. So let's check this out, because it sounds impossible, I know. But take a look at this. So what I have here is some water in a flask on a heat source. So the heat source is going to give that water lots of extra energy. So the water itself is going to be quite high in energy. So that's the first step. Then we're going to take the hot water off of the heat source and kind of get it back to just a little bit cooler down. We're going to cork it and then just cool the flask a little bit so that the cork is really stuck in there. And then turn the flask over. We're going to put it in a ring stand just to kind of hold it. So the water here has lots and lots and lots of energy. And then I've got some gas in here as well, above the liquid now. So I'm going to put the ice cube on and going to actually cool down this gas. So less energy of this gas. And then look at what starts happening to that water. The water looks like it's boiling again. So I'm not doing anything to the water. I'm cooling down the gas above it. So with your group, think about it. Well, if I cool down this gas, what does that mean about energy? What does that mean about pressure? And then why do we see that water start to boil? Just by putting ice on the top where the gas is. So that's what your group is trying to figure out. It's not magic, this is science. How am I able to boil that water by putting a cold ice cube on top of the flask by the gas that's above the hot liquid? Think about that for a little while. Not magic, it's science. And then go ahead and pause the video again, and we'll check in here in just a little bit. All right, so you know a lot now about you know a lot about liquids and gases. What we're going to talk about next is a little bit about how do we get from liquids to gases, liquids to solids. We're going to talk about how we get from solids to liquids. We're going to talk about melting. And so the first thing I want to talk about is just to review what melting is. So melting is when, of course, you go from a solid to a liquid. So if your solid particles look like this, they collect energy, and eventually those solid particles don't sit still anymore. They have so much energy they can start to roll around. They break the attractions, the really strong attractions between them, and they start to roll over. They don't spread out completely because there's still some attractions, but now they can kind of roll over each other. So now let's use that idea and apply it to why is there a difference in melting point between ionic versus covalent. So an ionic compound has that three-dimensional structure. You've got negative, positive, negative, positive, negative, positive, 3 dimensions. So you get a 3D structure. So that means that this one positive ion, cation, is not only attracted to the one next to it, but below it and above it and behind it and to every side. So you've got lots more attraction. Well, if I'm trying to break those attractions so the particles can roll over each other, it takes a lot more energy. Look at this one ion right here. It has to break attractions from this particle and this particle and this particle and this particle, the one that would be in front of it and the one behind it as well. It has a lot of energy needed to break those attractions, Well, as the energy gets higher and higher, the temperature would be higher and higher until those particles can actually start rolling over each other. So that 3D structure creates more attraction, and so it takes more energy to break those attraction. And then there's the correlation between energy and temperature. More energy means higher temperature before those particles will actually start to melt. In a covalent structure like this is a covalent molecule, this is a covalent molecule, this is a covalent molecule. In that sample, you have a lot less internal attractions. This molecule is barely attracted to this molecule. So it takes less energy to get this molecule start to roll so that it acts like a liquid. So it doesn't take a lot for this to start to roll or this to start to roll, and then my whole sample is rolling and it's acting like a liquid. So because there's less internal attractions when you have a covalent molecule, it takes less energy to start to roll, so the temperature of melting is actually much less. So this is the idea between the covalent and ionic melting points. So maybe you want to draw a little picture on your page to kind of help you remember those reasons why the melting point is so different. And when I say different, I mean like hundreds of degrees different. Like ionic solids can melt in the 800 and 900 degrees Celsius, and covalents sometimes are just at room temperature. They're already liquids. So that's kind of a cool thing about the difference in structure, not just like a couple degrees, but hundreds of degrees. All right, so once that makes sense, go ahead and pause the video again, and then call me over when you're ready to talk about allotropes. All right, here we go. We're on page 12. The allotropes I want to focus on are carbon. If you looked up the definition, again, an allotrope is just a molecular form of the same element, just different structures. So these are 3 structures of carbon that all at room temperature would be just carbon, but their structures are so different you end up with really different properties. So you've got soot, diamonds, and graphite, all just made of carbon. This is called fullerene, named after Buckminster Fullerene, who was studying this. And this is like after you burn a candle, like that black filmy stuff that is left over, that's soot. This is what the structure of that looks like, just carbon, and then you've got all this empty space, kind of complicated. It actually looks like a soccer ball. It is hexagons and pentagons alternating to create that curve shape. Diamond, you can see, has sort of this cubic structure, but 3 dimensions. This is what it looks like from the top, from the side, kind of from a different side. Really intense connections between them, really complicated. So that's why diamond is so strong. Versus graphite, that's the stuff that's in your pencils, just layers of carbon. So think about obviously how easy it is to write with your pencil because pieces or slices of that graphite just rub off very easily, just layers of graphite. So here's you can kind of see it from the side, from the top, another kind of side view to kind of see what that's looking like. So not as much connections between the layers, which is why they break off so easily. Not as complicated as this, where you've got this big open space, so it's really messy and sticks to stuff. And then that diamond structure, that repeating structure that gives you that really hard resulting structure, crystal. So these are allotropes of carbon. Thanks for listening. Go ahead and pause the video and check in with me when you get to page 14. Okay, so you should know some stuff about specific heat capacity, which just kind of general means how much heat can an object absorb before it starts to change its temperature. So with that, I'm going to go ahead and represent this with a great video called Burning a Cup or Not. So I'm going to do 2 versions of this on the video. You're going to see a cup full of air, and then you're going to see a cup full of water. And we're going to see a difference in the results because of what it is filled with. So here we go. So here is a cup that is full of air, so not really empty, but full of air. Put it over a Bunsen burner, and as you would expect, starts to burn, actually flames. So safely we put it out in a beaker of water. Now this is full of water. Still same thing, same kind of cup, putting it over, and you see that you don't actually see the same results, all right? Like very different results. So this one's full of air, and this one was full of air, this is full of water. Exact same demo, but a hugely different result this time. So with your group, I want you to be thinking about what is going on. How come this paper cup doesn't burn when it's full of water, and why does this one burn when it's full of air? And your hint is that it has something to do with specific heat capacity. What's really absorbing the heat, and what must be different about those specific heat capacity? All right? Excellent. So once you kind of have a handle on that, go ahead and pause the video, asking for any help as needed. Check back in when you get to page 16 about the phase change triangle. All right, so go ahead and draw this on page 16, your phase change triangle, and then there's 7 words to fill in on this page: melt, freeze, evaporation, boil, condensation, sublimation, and deposition. So depending on what's happening in this direction, so this is adding energy, the green arrows, and this is removing energy, the pink arrows. Go ahead and fill in those things. And like it says, there's only 6 arrows because one arrow will have 2 of those 7 words on it. So knowing some information about as I increase energy, that's the green arrow. As I decrease energy, those are the pink arrows. Go ahead and fill that in. All right, and when you're ready, then go ahead and pause the video, and I'll check in with you again when you get to page 17. All right, ready for your second to last diagram, the last one you get from the book. So this is a phase change diagram, and as you can see, this is as heat energy increases compared to when temperature increases. And so it's kind of giving you some hints about what state of matter you would have here, and then what's going on in this way. What state of matter would you here, and then what's going on right here, and then what state of matter would you have here. So you've got 2 different versions. If you are removing energy, like the energy is going this direction, what would you call that? And if you're adding energy, what would you call these things? So there's 4 words to add to this. So 2 of them take place at the same place on the graph. It's just whether or not you're adding energy or removing energy. And then the other 2 take the same place at the graph, whether you are adding energy or removing energy, to kind of understand a little bit more about phase changes. Go ahead and fill that in. Ask for any help as needed. And at this point, then, you are ready to finish the packet. Ask any questions that you have. We have a quiz coming up, so just ask Miss K for the specific date because it might change from the time I made this video. But thanks so much for listening. If you have any questions about kinetic theory, of course, check in with Miss K or whatever teacher you're working with. But I hope that this made a good amount of sense, and you understand the states of matter, solid, liquid, and gases, and all related to it much better. Thanks for listening. Bye.